What we do today is actually to move up one layer in the protocol stack and to start looking at what is called the networking layer, okay, of the ZigBee protocol stack. Okay. So again, on this figure, which I already showed you at the very beginning of the course, this is actually representing the reference architecture from the protocol point of view of the ZigBee communication stack. Okay. And as I was saying before, till last time, we actually know how the bottom two layers work, namely what is the physical layer and what is the rules to, let's say, manage the access to the shared channel. Okay, this is part of the 15.4 standard. Okay, what we do today is to look at this box here, which is called network layer. Okay, where basically we expect to find all those functionalities which deal with networking or internetworking, meaning how to actually deliver information remotely, okay, through multi-op paths. Okay. To be 100% precise, the ZigBee specification, which starts from the 15.4 above, also includes, as this figure represents, a part which is called application interfaces. Okay. Why? Because ZigBee, besides specifying the networking, let's say, rules and protocols, it also, as we will see, provide hooks, provide APIs, okay, for the application developer. Namely, it provides a very, very tight and strict, let's say, vocabulary dictionary, okay, for the application implementer developer to actually implement applications. Okay. So let's focus here on this network layer. Okay. What do you expect to find in the network layer? Which are the main functionalities of the network layer, of any network layer you are faced off?
How is the topology?
Right, routing, topology, which is kind of the same thing as routing, so how to manage the topology. What else? What kind of services you expect to find in a network layer? Okay. What kind of services you have in IP, in the internet protocol? You have routing. Okay. What else?
IP.
Huh?
We have IP here.
IP what?
IP here. IP internet.
Right. Well, what kind of service you have in IP?
Controlling header, say what kind of packet.
Okay, so basically it's two services, okay, which any routing protocol must have, I would say. First one is addressing, so it should provide unique addresses to all the nodes in the network, okay. And the second one is routing, meaning it should somehow tell any node, any networking node of the network, what to do of the information it is processing. Okay. Always remember that information here means packets. Okay. We are always concerned about packet switch networks. Okay. So lesson of today is dedicated to how routing happens in ZigBee and how addressing happens in ZigBee. Okay. Besides these two main functionalities, the ZigBee network layer also provides some additional services and functionalities, okay, which are listed in this slide. Okay. For example, routing and route discovery are actually also neighbor discovery are all, let's say, all functionalities which are relative to routing problems. Okay. So whenever you have to route information, okay, the first thing you have to do is to discover where you are. Okay, meaning you have to know who your neighbors are, so which is the nodes closest to you. Okay, and this is usually called neighbor discovery. Okay, then you have to be able to discover also nodes which are not close to you, so which are not, let's say, one of neighbors to you. Okay, and this is always or often called route discovery. Okay, meaning besides knowing who is close to me, I also need to know who is not close to me. Okay, meaning I also need to know all those nodes which I can reach in multi-hop kind of paths. Okay. And then the third functionality which deals with routing is routing per se, which is actually the ability, once you know where you are, so who are your neighbors, and once you know which, let's say, path to follow to reach, let's say, faraway neighbors, okay, how to enforce these paths, which means how to, let's say, transfer the information according to these paths. And this is, let's say, the core of routing functionality. Okay? And then you have already the already mentioned addressing functionality, which means that we must be able to address in a unique way, okay, all the nodes in the network. Okay. Let me repeat it, in a unique way, which means that we cannot have, okay, two network nodes which share the same address. Okay. Why not? Because routing is based on addresses. Okay. Which means that if two nodes have the same address, okay, routing functionality cannot actually work, okay, because it cannot find what is the path towards the specified destination, okay? And then we have a bunch of, let's say, bootstrap or startup functionalities which deal with the network startup, okay? So the network layer of ZigBee provides functionalities for starting a network. So how a node can just be switched on, okay, and actually can start a new network, okay. We must have functionalities for joining, for managing the dynamics of the network, meaning that we must have procedures such that a new node can actually be part of the network, okay. We must have procedures such that a node which is willing to leave the network can do that, okay. And we must have actually procedure to handle the rejoining. So a node which we already know, okay, must be able to re-enter the network if he or she had left beforehand. Okay. So all this stuff here is actually functionalities which are dealing with the network topology formation or bootstrap or startup. Okay. Clear? Obviously, as we will see, in the startup phase of the network, so once the network is started up, or when a new node is accepted in a new network, or in an existing network, okay, then at the same time of this, network startup phase, we must handle addressing, routing, route discovery, and so on and so forth. Which means that all these functionalities have interdependencies among each others. Okay, clear? But again, the core ones are routing and route discovery and neighbor discovery, which we will see in short. Again, in a very, very few lines, which are the components of a ZigBee network? Okay. Always remember that components here means elements at the networking layer. Okay. So the main building blocks of the ZigBee networks are the nodes, okay, which again, as already happened for the 15.4 standard, are organized with some kind of hierarchy. So they're not all the same, okay, but they have specific functionalities, meaning that there are specific classes of nodes which have specific functionalities, okay. And in particular, the specification, the ZigBee specification, defines three kinds of nodes, three classes of nodes. The first one is the ZigBee coordinator, okay, which is actually responsible of coordinating the network at the networking layer, okay. And usually, this ZigBee coordinator is equivalent to what we have called full function device at the 15.4 layer. So the full function device also plays the role of the ZigBee coordinator, okay. And usually, the PAN coordinator often plays the role of ZigBee coordinator. So who manages the network at the medium access control layer, okay, also manages the network at the network layer, okay. Then we have the so-called ZigBee routers, okay, which usually are full function devices, okay. And then we have the so-called ZigBee end devices, which usually are, can be whatever. So they can be reduced function devices or full function devices, okay? So what's the differences between these three guys? As I was saying, this one is the boss, so this one is the coordinator of the network, okay? Which means that it can run all the functionalities of the network layer. So it has the full network layer, let's say, functionalities. These guys here are routers, which means that they can actually play the role as relaying devices. So they can actually relay the information which is not generated by themselves, but which is received by someone else. Okay, so these are basically equivalent of internet routers, internet networking devices. Okay, these guys here and devices, they basically have a reduced network layer, which means that they do not implement all the functionalities of the networking layer. Okay, and the only functionality they can actually implement is actually addressing and all those services related to joining and leaving the network. Okay, in other words, they cannot play routing, so they cannot route information. They can just produce information, okay, towards the ZigBee coordinator. Okay, clear so far? So one last comment, as you can see, this kind of hierarchy basically reflects the hierarchy we had at the lower layers. Okay, we had the PAN coordinator, we had the full function devices, and then we had the reduced function devices. Okay, here basically the relation is one-to-one. Okay, PAN coordinator is a ZigBee coordinator, full function devices are routers, ZigBee routers, reduced function devices are ZigBee end devices. Okay, so what kind of routing? So how routing is actually managed in ZigBee? We have two actually flavors of routing. So we have two protocols which run aside. Okay. The first one, which is the basic protocol, is called a cluster tree algorithm. Okay. The second one is the ad hoc on-demand distance vector, which I guess you have already seen somewhere else, right? Do you know AODV? Yes? No? No? I guess that you will see this kind of protocol in other courses here, okay, and in particular in the course on wireless networks, I guess. All of those of you which are attending those that course. What's the difference between the two? We will see them both in details in a few seconds, but just to anticipate you the difference is the following. This one, the cluster tree algorithm or the cluster tree routing approach, creates a tree, meaning that the information is delivered, okay, along a tree towards one specific, it's called sink, okay? And as you will see, the tree which this protocol here creates is rooted at the ZigBee coordinator, okay? So in the cluster tree algorithm, you have a tree which is rooted at the ZigBee coordinator. So the ZigBee coordinator is the root of the tree, is the first node of the tree, okay? And then all the other nodes, let's say, use paths to deliver information which follow a tree, okay? So the routing pattern is a tree. I guess that all of you know what is a tree, right? You know what a tree is? Okay. Not those one outside, but trees on graph, okay? Okay. The AODD, okay, is basically creating mesh topologies, meaning that the route or the routes which are used to deliver information, in principle, okay, can be meshed ones, meaning that we don't have any structure of the, let's say, routing topology, which is enforced, like the 3-1 in the second protocol, okay, but rather the paths can be meshed ones, depending on specific conditions of the network. Okay? Again, we will see the two in details in a few seconds. So let's start from the basic one. So let's start from the cluster tree algorithm. Okay? Why you think that the basic routing pattern is a tree in sensor network, in ZigBee? Why? question is why enforcing tree-like structure to manage routing in ZigBee, in sensor network in general? Why not using any other kind of graph topology as a basic, let's say, protocol?
Because some of our nodes are RFD, so the tree topology would be better for them because they are not fully functioned. They just want to communicate with one node, so they will be the leaf of tree, and it's I don't know how to explain.
Okay, I rephrase. The reason is that most, as I was saying, I guess, sometime back, most of the traffic here is going through one single sync point. So most of the traffic in this kind of deployments, in ZigBee deployments, goes to one single point, which is the ZigBee coordinator or the sync or the PAN coordinator, call it whatever you want. Okay. And whenever you have to manage traffic which goes in one, let's say, sync only, okay, the easiest and most efficient way you can do that is by enforcing a tree structure, which is rooted at that very sync point. Okay. Then, as we will see, because it's easier to actually implement routing along trees. Okay. So let's see in a few slides how this cluster tree and tree formation process works. So everything starts from the, let's say, a full function device. So a node is activated, and this node is a full function device according to the 15.4 classification, which means that it is the most powerful node in our network, or one of the most powerful nodes in our network. Okay. So what a full function device does to set up a network and then create a tree is first to scan all the available channels which you can use, okay, for operation, and this is somehow accomplished by resorting to the lower layers functionalities, which we have seen in 15.4, the scanning functionalities. So once this full function device has chosen the best channel to access or to use to start up a network, it can set its own transceiver to that channel. Okay. It can decide what is the person area network identifier, which is the unique ID of the person area network according to the 15.4 specification. Okay. And then it sets its own network address, which is a ZigBee kind of address, to 0. That's by default. Okay. So the let's say ZigBee coordinator, which is the PAN coordinator at the lower layers, has a network address which is by default set to 0. Okay. Now the network is on, which means that depending whether the node is operating in beacon-enabled or non-beacon-enabled mode, it will start sending beacons periodically, for example. Okay. And it will start signaling in these beacons its own PAN identifier, so the identifier of the network, and its own network address. Okay? So all the other devices which are around the coordinator, they may now associate to this guy here, okay, using again lower layer procedures which we have seen last time. Okay? And these guys which associate to the PAN coordinator, they may be full function devices which play the role of routers, which means that they can actually implement routing functionalities, okay? Or they can actually be only ZigBee devices, which means that they cannot relay traffic which belongs to any other node in the network, okay? Address assignment, so once a new node is associated to the network, which means after a new node has completed the association procedure, okay, with the PAN coordinator or ZigBee router, okay, the ZigBee coordinator assigns at the same time of the association procedure to this node a ZigBee address, and ZigBee addresses are 16 bits short addresses, okay. So once a node is associated to the network, at that same time, it has a ZigBee address, which is a 16 bits long address, which can use to actually route information. Okay. Clear? Okay. That's for, let's say, the first node, let's say the first tier of node associating to one pan coordinator. Okay. Always remember that the goal is to create a tree topology. Okay, which means that other nodes can now associate to the network via some kind of relaying nodes or router nodes. Okay. So basically, the trick is that the ZigBee coordinator or the ZigBee router node assigns to any other node which is willing to associate to the ZigBee network, okay, not just one address for the node itself, but a group of addresses, okay, which actually is used to address all the nodes in the branch of the tree which is rooted at this, device which is accessing the network. Okay, clear? Let's see it in more details. Okay. So what I'm saying is that if, for example, this is the ZigBee coordinator, okay, and this guy here has two nodes which are associated to the ZigBee coordinator. Okay, the ZigBee coordinator gets address 0. Okay, and for example, these two nodes here, okay, they are assigned addresses to by the ZigBee coordinator, okay, for themselves. For example, this is 1, okay, but also for the branch, for all the branch of the tree which is rooted at this guy here. So the ZigBee coordinator tells this guy, okay, you can use address 1, and for addressing all the nodes underneath you, okay, you can use 2 and 3, okay. And the same stuff for this guy here. So the ZigBee coordinator assigns blocks of addresses to nodes such that these blocks of addresses can be assigned iteratively, okay, to nodes in the lower parts of the tree. Okay, that's the idea. Now we'll see the details. Okay, is it clear? Okay, so let's define some names which are used to define the address assignment in tree. Okay, and the names are following. So any ZigBee topology is characterized by, I would say, 3 parameters. The first one is Rn, okay, which is basically the maximum number of routers at any layer of the tree. So any layer of the tree cannot have more than Rm routers. So Rm devices, meaning any layer of the tree cannot have more than Rm devices which can relay information. Okay. Then the other parameter is the number of n devices, which is d of m. Okay, and as the name says, this is the maximum number of devices for any layer of the tree, which are actually n devices. Okay, and then you have the last parameter, which is L of m, which is the depth of the tree. So how many layers you have in your tree. Okay. All these parameters are, let's say, managed by the ZigBee coordinator. So it's the ZigBee coordinator which in the network bootstrap phase, network startup phase, signals this parameter downwards. Okay? So they are somehow prefixed. Okay? You can take them as prefixed. Okay? So for definition, by definition, depth 0 is the ZigBee coordinator. So the layer 0 is the ZigBee coordinator node. And then as you go down, you may have different layers at different depths, meaning at different distances, okay, from the ZigBee coordinator, the root of the tree. Okay. Any layer in between the, let's say, last layer, the leaves of the tree, and the ZigBee coordinator is composed, okay, of a number of network nodes, routers, ZigBee routers, which can be above R of m, and the number of n devices which cannot be above d of m. Okay, that's the definition of. That's the parameters which define the tree topology. Okay. So let's see how addressing works. Idea is the one I've sketched here. Okay. This idea in formulas is something similar to what you see in the slide. Okay. So this slide reports the, let's say, sites of the block of addresses, okay, which are assigned to any node at a given layer in the tree, okay, where D is basically the depth of the tree we are looking at. So D0 is the ZigBee coordinator, D1 is the first layer of the tree, D2 is the second, and so on and so forth. Okay. So D spans from 0 to L of M, which is the lower layer of the tree. So it's the leaves of the tree. Okay? And the function A of D just tells you how many how many addresses a ZigBee router at level D must have for addressing itself, for himself, and for all the nodes which belong to the branch of the tree rooted at itself. Okay? Clear? So let's, for example, take the first case. So the first case is where we are looking at nodes which are at the second last layer of the tree. Okay, so these nodes, these router nodes, are the nodes which are basically, in this case, here. Okay, so in this case, on the blackboard, you have a tree with 2 layers. So L of M is 2. Okay, so we are looking at nodes which are here, at the second last layer of the tree. Okay, so what this formula, or the first, let's say, instance of this formula is saying is that these guys here, so these guys at the second last layer of the tree, okay, they must have an address for themselves, which is 1, okay, plus an address for all the nodes in the branch of the tree they are actually managing, okay, which is, in this case, for node number 1 here, okay, is 2 and 3, okay. Again, the nodes in the second last tier of the tree, they must have one address for themselves, plus one address for all the DM and devices which belong to their own subtree, okay, plus an address for all the router nodes which belong to the to their sub-branch of the tree. Okay? Clear? And then, if you understood this first, let's say, instance of the formula, understanding the second one is fairly easy because it's the same, let's say, process with the difference that the node at any layer of the tree, which is not the second last one, they need an address for themselves again. They need an address for all the end devices which are directly connected to themselves. But they also need an address, okay, for any node in the sub-branch of the tree, which is managed by the device itself. Okay, so just to make it more clear, suppose you have a structure like this. Okay, this guy here, what the second instance of this formula is saying, okay, what this instance of the formula is saying, is that a node here, for example, so a node at layer 1 of the tree needs an address for himself. It needs an address for all the devices which are directly connected to itself, which are end devices. Okay, but it also needs an address for all the devices which belong to the sub-branch of the tree. Okay, and this is expressed by this recursion, okay, which is A of D plus 1. Clear? Another way. A device at level D of the tree, okay, has R of M children, which are routers themselves, okay, and each one of these child router needs a block of address which is A of D plus 1. Okay? Clear? Questions? So, this stuff here tells you, you tell me what is the layer a ZigBee router is in, okay, and I tell you what is the block of addresses which you have to assign to this guy, okay, such that it can address itself and all the sub-branch of the tree, okay? Obviously, all the nodes at that L of m, so all the nodes which are the leads of the tree, they just need one address, okay, because they don't have any further layers underneath, okay? Then there is this simple assignment rule, which is once I know what is my block of addresses, okay, so once a ZigBee router knows which are the addresses it can actually use for himself and for the other guys underneath himself, how these addresses are assigned, okay, and this is the official, I would say, assignment rule of ZigBee. That's very complicated, okay, sorry. If you look at it, it's complicated. If we see an example, it's very easy. So let's say move to example, which is fairly much easier to understand. Okay. Example. Suppose we have this kind of topology. So we have a tree depth of 3. So we want to enforce a tree structure with maximum 3 layers. Okay. And at each layer, we have 2 router nodes, and we have 2 maximum end devices. Okay? So let's apply the formula which we have commented in the previous slide to this very case. Okay? Let's start from the lower layers. Okay? So for example, let's start from A2. 2 here is the second last layer, or 3, because the tree has 3 layers maximum. Okay? So A of 2, which means all the routers which are at the second last layer, okay, they only need addresses for themselves and their children. That's it. Okay? So they only need one address for themselves and one address for all the children of this guy which belong to the last layer. Okay? How many children one router has at the last layer? It's just R of m plus 0. 2 plus 2. Okay? Example, this is a second last ZigBee router. So router 15 here in the figure is a second last ZigBee router. Okay? And by definition, it only has 2 children which are routers, 16 and 17, and 2 children which are end devices, 18 and 19. So it just needs 5 addresses. Okay? Clear? Okay, so let's move up one layer. So let's see what happens at routers at layer 1. Okay? Routers at layer 1 are, for example, let's see them on a picture. Router at layer 1 is, for example, this router here, 14, right? This is one ZigBee router at layer 1. This guy here must be assigned one address for all the nodes which he somehow manages, meaning that he must have an address for himself, okay, and an address for all the branch of the tree which is underneath himself, okay? In formula, this means that this guy needs one address plus 2 addresses for the end devices which are children of this guy here, okay, plus one block of addresses for all the ZigBee routers which are node 15 and node 20, which are children of node 14. Okay? But the number of addresses needed by router 15 and 20 is exactly what we have found at A2. It's exactly what we have calculated as being A of 2. Okay? So in formula, A of 1 is one address for the router itself, plus 2 addresses for the 2 end devices which are children of this guy, plus all the addresses which are needed by all the ZigBee routers, which is 2, which are at the lower layer, which is A. Okay? So in total, we need to have 13 addresses assigned to this guy. Clear? Then, if you iterate the same stuff, you go up to A0. A0 means how many addresses are needed in the network. So at layer 0 of the tree, which is at the ZigBee coordinator layer or level, okay? You apply the same recursion, okay, in the sense that you can say that the PAN coordinator, sorry, the ZigBee coordinator needs to have 2 addresses for its own one of children, plus 1 address for itself, plus all the addresses which are needed to support 2 more ZigBee routers, which are 1 and 14. Okay, how many addresses is this? Is basically A of 1. Okay, so each one of these 2 ZigBee routers, 1 and 14, they need to have A of 1 addresses themselves. Okay, that's why we have this recursion according to which A of 0 is 1 plus 2 plus twice A of 1. Okay? Clear? So in total, we have, for this kind of network, 29 addresses which need to be distributed, assigned in the network, to the network nodes. Okay? So this is, let's say, the application of the formula which we have seen before. So how addresses are assigned, or sorry, how many addresses are assigned to nodes. Okay. If you look at the figure, you have an example also on how these addresses are assigned. Okay. In the sense that if we start from 0, so if we start from the ZigBee coordinator, okay, we know that this guy here has a set of addresses which can be assigned, which spans from 0 to 28, which is 29 addresses in total. Okay, 0 is taken by the node itself. Okay, and then the remaining part is assigned to the children nodes. Okay, and the assignment process is the following. So the first address, excluding 0, okay, is assigned to one of the 2 ZigBee routers, which are children of 0, like this guy here, okay? And all the remaining addresses, okay, are first assigned to the sub-branch of the tree of this first router here. For example, in this case, the ZigBee coordinator is assigning address 1 to this guy, okay? And it's also telling this guy you can use addresses from 1 to 13. Okay? So the addresses are assigned in blocks in a kind of round-robin fashion to ZigBee routers first. Okay? And then what is remaining is addresses for the ZigBee end devices. For example, in this case, the coordinator will have 2 end devices which use addresses which are at the tail of this address set here. So 27 and 28. Clear? Obviously, there can be other, or there are other ways you can actually assign addresses to nodes. Once you know how many addresses you can have, there are several ways you can actually assign addresses to nodes. Okay. This one is the one used in the ZigBee specification. Okay. So first, give out blocks of addresses to ZigBee routers, okay, and then accommodate ZigBee end devices at any layer. Okay? Clear? Questions?
Is it possible to have the same nodes in the same layer with different sub-branches? For example, 14 has 2 end devices and maybe 1 has 1 end devices.
Question is it possible to have unbalanced trees, like some node with fewer end devices or more end devices? Answer is yes. Okay. However, the blocks of addresses are always assigned according to the parameter R of m, D of m, and so on and so forth. Which means that you can have a node which has, for example, one router less than another node, okay, but still this node has the same number of addresses available, okay, for assigning new nodes, okay. So, in other words, R of m, D of m, and L of m are the only three parameters which are used in the address assignment. Okay? Regardless how many nodes you have in the network. Okay. Other questions? Okay, so fine. We know how the tree is built up. Okay. Let's see how routing happens. Okay. So one thing which I've mentioned. One thing it's worth mentioning with more strength is the following. This way of giving out addresses, so this way of addressing nodes, can actually be used also for routing. In other words, if all the nodes know how addresses are actually assigned, okay, by knowing their own address and their own, let's say, place in the tree, okay, they know they have all the information to actually know who is their children, okay, who is their parents, and so on and so forth. Okay, meaning that this guy here, okay, knows that its own address is 7, for example, okay, and by knowing that this address is 7, it knows that its own address belongs to the address block, which is referring to this node 1 here. Okay. So just by knowing its own address, they know exactly where they are placed in the tree. Okay? Because addressing, again, is totally governed, managed by these fixed parameters, which are R of m, L of m, and D of m. Okay? So, in a sense, routing can actually be implemented just by knowing, okay, its own address, or just by knowing where any node is placed in the tree. Okay? And that's exactly what happens in the tree-based routing protocol of ZigBee. Okay? That's the very, very stupid, let's say, procedure for implementing routing according to the tree-based routing in ZigBee. Okay? So what any node must do is to check out whether the destination address of the packet it is managing, okay, is one of the addresses which belong to its children. Okay. How does it know it? Because addresses are again fixed. So if I know my address, I know exactly who are my children addresses. Okay. And if this is the case, they can actually route the packet directly. Meaning that if the destination address of the packet I'm managing is one of my children, I can just route directly the packet to these children here. Okay? If not, okay, I have an else here. Okay? If the destination address belongs to one of children routers addresses set, meaning that it's not meant for any of my one of neighbors children. Okay? But I know that the packet is the packet is meant for example, one of the children of one of my ZigBee routers children. Okay? If this is the case, it means that the packet must be routed down to my own tree branch, okay? Which means that the router can actually send the packet to the corresponding ZigBee router children. Okay? Here. It's this case here. So this guy has a packet which is not meant for any of its own two children, okay? But just by looking at the address, this guy realizes that this destination address belongs to the address set which it has assigned to this guy here, okay? So it just forwards down the packet to this guy here, okay? Clear? The last else here means that the packet is not meant for downwards, meaning that the packet is not meant for any of the children of the node which is processing the packet, and it's not meant for any of the children of the ZigBee routers which are children of the node which is managing the packet. Okay? In other words, the packet is meant for upwards Okay, it's meant for another branch of the tree. Okay. In this case, the only thing the node can do is just to route up the packet to the first ZigBee router, which is its parent. Okay, which is this case represented here. Okay, the packet, for example, this guy here has a packet which is meant for this guy here. The managing node of the packet and the destination, they are not in the same branch of the tree. Okay, how can this guy know that they're not in the same branch of the tree? Because the destination address does not belong to its own address block. Okay. In this case, what this guy does is just to route up the packet to the first ZigBee router at the upper layer in the tree itself. Okay, clear? So, as you can see, once you have assigned the addresses in the way I've shown to you, okay, routing along the tree is very, very easy. It's fairly easy. Okay, you don't really need to have any routing table, right? You know what the routing table is, right? Why you don't need any routing table here? A routing table is something which tells you for any destination address what is the next stop you have to implement. Okay. In this case, you don't need any routing table because you actually enforce the routing to happen along the tree, and you know by construction of this tree, okay, where your destination is. Meaning, it's directly whether the destination is directly connected to myself, whether the destination belongs to my sub-branch of the tree, or whether the destination is someone else. Okay, it's the only three things you have to know, or you can actually know, just by looking at the addresses. Okay, and if you know these three things, you can just route very easily, okay, according to one of these three cases here. Okay, direct connection, downwards or upwards. That's very easy. Okay, and that's the very reason why they actually chose this type of routing. Okay, so they chose this type of routing because you don't really need to keep routing tables. Okay, routing tables may be costly in the, let's say, amount of storage which you can have. Okay, so if you want to reduce at the minimum the number of information you have to store to implement routing, okay, that's the way to go. Okay, so to manage routing through trees and by assigning properly the addresses to the tree nodes. Okay? Questions? Yes? Okay, question is, why do we have routing nodes at the last layer of the tree? Reason is that you can actually extend the tree. So you can start a new network with a L of M parameter which is fixed, say it's 2, okay? Then you realize that you need more depth in the tree, okay? So you may want to extend the tree, and extending the tree means that some nodes at the leaf of your previous tree must play the role of routers. So you might have the need of having routers at your very last layer of the tree. Yeah? You have to, yeah, in that case, you have to redo addressing, yes. You have to, yeah. You have to replay the addressing, so reassign addresses if you assign nodes, yes. Other questions? Okay. Yeah?
How does the prank coordinator understand that the node, for example, join the network?
Okay, so question is, how does the PAN coordinator know that the new node is joining? The answer is because there are procedures at the 15.4 layer to handle the association phase. So if you remember when we talked about 15.4, in beacon enabled mode, for example, okay, the PAN coordinator is beaconing, okay, and is signaling in the beacon, okay, whether it is willing to accept new nodes as new node associating to the network or not. Okay, if this message is 1, meaning punch coordinator is willing to accept new node, a new node can actually, in the collision access part, if you remember, okay, issue an association message or association request message, okay, which is forwarded up to the punch coordinator. So it's lower layer procedure, let's say, which are managed by the 15.4 standard. Okay. So the pros, so the advantages of this kind of approach for routing is like, again, simplicity. So it's very easy. It allows to avoid having routing tables. Okay. The disadvantages is basically yeah, it's not optimal in the sense that, as it's written here, is quality agnostic, meaning it does not take into consideration the quality of the links. Okay. More than that, it does not even take into consideration the existence of the link. Okay. That's very, I mean, what you see in the picture is very, very representative example on the inefficiency. Okay. Okay, so yeah, in this case you span 4 transmission against the only one which you could span. Okay, so the tree-based routing is non-optimal from the, let's say, point of view of the routes. So you might have perhaps routes which are longer than what needed. Okay, and more than that, this kind of routing does not take into consideration the quality of the link. Okay, so any link here has the same quality, is, let's say, assumed to have the same quality as all the others. Okay, which in this case might not mean, in the case of sensor networks, might not be, you know, very representative of reality. So you might have links which are more, let's say, performing in terms of bit error rate or packet reception rate and so on and so forth. But this kind of routing here does not account for, let's say, distinguishing the quality of links, okay, or better, defining routing metrics which distinguish the quality of the link or consider the quality of the link. Okay? Questions? Okay. So so that's the basic routing scheme. In reality, what you see in the picture is what is implemented. So what is the routing process implemented in ZigBee? Okay, what we have discussed so far is the tree-based routing, which is basically the fallback routing procedure. So what you do if you cannot do any better. Okay. If we start from above, you have to route a packet. That node up there means that we are at the ZigBee router and we have to route a packet. Okay. So what you have to do is basically to check first whether the packet has reached destination. So the node which is running, which is processing the packet, is actually the final destination of the packet itself. Okay. In that case, the routing is aborted. There's no routing, okay, any longer. Okay. And we are at this block here. Then, if we pass this test here, meaning the packet is not meant for locally, okay, but the packet is meant for one of the devices which are neighbors of the node processing the packet itself, okay, so one of neighbors, okay, then again routing is aborted and the packet is transferred to that specific device, okay. So the first 2 blocks here are the easiest cases where either the packet has arrived or the packet is just one hop away to destination. Okay. Then we enter this block here, okay, which is again applying AODD routing. Okay. So if the packet has not arrived yet, okay, the first option you try to put in place, the first way you try to route the packet with is through AODD, okay? And then, if AODD fails, for any reason, okay, you fall back to tree-based routing. So you do what we have commented till now, okay? Now we just have a look at how this block here is implemented. So what is the AODV routing approach in ZigBee? Okay. So this was just to tell you, fine, what we have told so far is just a fallback option, okay, which is routed along the tree. Okay. The first option is AODV routing. Okay. I also have to say that in most of the implementation which I've seen, okay, this block here does not exist. Okay. So in most of the implementation I've seen, they go down directly to tree-based routing. Okay. Why? Again, because it's simple, because traffic is mostly upwards, so towards the sink, so you don't really need to have cross traffic, among nodes, and so on and so forth. Okay, I would say 80% of the implementation just use tree-based routing. Okay, and only 20% they have the full stuff here, so they have the whole AODV plus cluster tree stuff here. Okay. Clear? Okay.
Why it passes to the variable?
Which one?
At the first section.
Okay, so here it means that you have received a packet, you check out whether it's meant for you. So you check out the destination address of the packet against your address. You have a match, which means that you have to pass the packet to the application. Higher layer means here not in the tree, but locally the higher layer in the protocol stack, which means the application layer. Okay? Clear? Okay, so let's see how AODV works. What I'm going to do now is just to first give you the high-level concept of how AODV works, and then we go into the details on how this is implemented in ZigBee. Okay? So AODV stands for Ad Hoc On Demand Distance Vector. Okay? Which means that just by looking at the name, you should expect that it somehow resembles some kind of distance vector routing protocols which you have seen in other courses, right? Have you seen any distance vector routing protocol in other courses? You know what distance vectors is, right? Yes. Who knows? Who does not know? Astenuti. So distance vector means that you don't really need to have the knowledge of the full route to a specific destination, okay? But rather the information which is exchanged for supporting routing is information on distances to destinations. So all the nodes, in principle, know how far they are from any specific destination. Okay, that's the core of distance vector process. Okay. However, this is on-demand distance vector, which means that in classical distance vector, you have basically periodic signaling of routing information. So periodically, a network node sends out the distance vectors, which are information including how far is the node from any specific destination. This is done periodically. Okay. In AODV, this is done on demand, which means that it is, the routing procedure, the routing process is triggered only when one packet has to be routed. Okay, it's not done periodically. Okay, that's the main, I would say, difference from, let's say, standard distance vector protocol. In few words, we have said that the process is on demand, which means that the route is discovered only when needed. Okay, and the route discovery is based on these messages, which are called route request messages. Okay, so a node has a packet to deliver to one specific destination. Okay, the destination is not known to the node itself, so the routing node has to find out what is the route to that destination. Okay, the first thing is for this node to issue a route request message. Okay, including the information on what is the destination which needs to be discovered. Okay, and this route request message is flooded, meaning is sent out in broadcast. Okay, to all the nodes in the network. Okay. Clear? So I have to reach that guy over there. I don't know where. I mean, I don't know what the path to that guy is. So I just issue a request to find a path to that guy, and this request is flooded by the network, meaning that all the nodes receiving a route request message just resends it to its own neighbors. Okay. In the end, the hope is that at some point of time, the route request message, which is relayed by all the nodes, will reach that guy. Okay? And that guy, the destination, recognizing its own address in the route request, will answer back with a so-called route reply message. Okay? Once the initiator of the procedure receives the route reply message, it gets to know what is the path to the final destination. Okay? How? Because all the nodes which are rebroadcasting the route request maintain a backward path, okay, to the previous node in the route request broadcast process, such that when the route request reaches the destination, the route reply can be sent back unicast, okay, over this, let's say, backward path. Okay? Let's see an example. Suppose we have our source of information is S here, okay, and I guess we want to send something to D, destination, okay. S does not know anything about D, so it means that it does not know where D is, okay. S can be either a source of information, so the information can be originated here, or it can be just a router which received the packet meant for D, but does not know yet where D is. So it's a routing entity, I would say. So the first thing S does, since it does not know where D is to issue a route request message, okay, and to broadcast this message to its own one of neighbors, okay. So in this case, the route request message is received by B, C, and E. Okay. What B, C, and E do, in principle, is just to forward again this route request. Okay. So they forward again this route request. Okay. For example, the route request received by C is forwarded to H, G, and E. Okay. And at the same time, they set up a backward path to the initiator of the route request process. For example, when E receives the route request from S meant for D, okay, besides sending out again the route request to F and C, it also maintains a pointer back to the initiator of the procedure. Okay, this pointer, which is this solid line here, is the one which will be used then by the route reply to go back unicast to the initiator. Okay? Then the process is iterated. So again, all the nodes receiving the route request will forward the route request again. Okay? And all the nodes receiving a route request will maintain or set up a backward path towards the node they have received the route request from. Okay? Obviously, if the same node receives route request from, let's say, different paths, meaning from different nodes, okay, only one single reverse path is maintained, and usually is maintained the best one. Okay, for example, this guy here, C, okay, receives a route request directly from S, okay, but it also receives a route request indirectly from E. Okay, but still the reverse path it maintains is the direct one, even if there are two of them. Okay, and the choice is based on the best path. We will see what best means. Best means the path which has the lowest metric. Okay, and the metric used for routing we'll see in the next slides. Okay. So in the end, the route request is received after some time also by D. In this case, we have two route requests received by D, okay, from J and K, okay. So D now can actually answer to the route request. Okay, and obviously, since this is the destination of this route request, it just refrains from broadcasting again the route request. Okay, just set up the reverse path towards J. Again, the reverse path is set up towards the best node, or better, using the best reverse path possible. Okay, according to this metric we will see in the next future. Okay. And then once the route request has reached the D, and once this reverse path is set, actually, okay, D can now reply to the route request by issuing a unicast, in this case, route reply, which follows the reverse path. Okay, so the route reply sent by D back to S follows the path J, F, E, and S. Okay, and once S gets this route reply, okay, it can just use the forward path again, so the backward path reversed, to reach the destination D. Okay, so the information can now be routed from S to E to F to J and then to D. Okay? Clear? And that's the data. I mean, that's exactly the path followed by the data. So path followed by the packets sent by S to D. Okay? Yeah.
The destination between the nodes are, if they are dynamic or they are changing, what will happen in that case?
What do you mean by changing?
I mean, for example, between S and E is 2 seconds, but if it changes, for example, there are some nodes that are moving. What happens?
Okay, so question is, what if the network topology changes on the fly? Okay. I mean, this is true for any routing protocol. So, and what is true for any routing protocol is that the, let's say, underlying assumption is that the speed at which the topology changes, okay, is lower than the convergence time of the routing protocol. Meaning that if S wants to send something to D, okay, it must be true that the topology does not change in the time frame needed to build up this path. Okay, if it changes, any routing protocol will fail. Okay, so always the inherent assumption is that the dynamics of the mobility or duty cycling or whatever, which changes the topology, is lower than the convergence time of the routing protocol. Okay. Otherwise, if it's not true, you cannot use any, I would say, signaling-based routing protocol. You have to use something else, which is opportunistic routing, but that's out of the scope of this course. Okay. But it's a good question. Then there are some, let's say, additional tricks and needs on AODV, which are actually dealing with the fact that once you receive a route request, you're forced to set up a backward path. Okay. For example, let me go back some slide. For example, this guy here, okay, is receiving a route request at through some path. Okay. So he's forced to maintain a reverse path towards C, for example, okay, even if it is not involved in any kind of transmission from S to D, because the transmission happens somewhere else in the network, okay? Which means that these pointers here, which are, let's say, lines in some routing table, actually it's called routing discovery table, okay, they must be purged, they must be erased, cancelled after some time, because there's no use to, block some resources in the memory of the node for keeping up a pointer which is useless. Okay? So this is just to say that these reverse paths have a validity in time. So after some time, all the nodes which have a reverse path active, which is a line in the table, they just purge this table, so they just erase this reverse path if this timer expires. Okay? In other words, all this process is governed, is managed by timers, as any other routing protocol you have seen in any other course here at Polytechnic. Okay? Why? Because again, there's no use to maintain routing information which is too old. Okay? So you after some time you just refresh all the stuff and you purge all the information which is too old. Okay? Let's see how this thing here is implemented in ZigBee. Okay, it's actually implemented through two tables, so we don't have just one table, but we have two of them. The first one is the routing table, which is exactly the same concept you have seen in other courses. So in this routing table you have a destination address, which in this case is 16-bit address, ZigBee, and you have a next hop address, which is again 16 bits. It's ZigBee-like addresses. Okay. And the additional information you have in this table is the entry status. So it's actually a flag which tells you whether that specific line is active, okay, is inactive, or is under discovery. Active means fine, you can use it. Okay. Inactive means you cannot use it, but it's still there. For example, for timing issues. Okay. And under discovery means that a route request discovery phase was launched for that specific destination address, but no next hop is already available. Okay, which means that the discovery is underway. Okay. And then you have the routing discovery table, which is the, let's say, piece of data which is used to build up the forward and reverse path. Okay? You have a bunch of columns in this table. The first one is the route request unique ID, which is actually a sequence number which uniquely identifies the route request which is referring to that line of the table. Okay? For example, if I receive route request number 3 from one specific node, okay, this field here will report number 3, sequence number of that message. Okay. Then I have the source address, which means who is requesting that specific route. Okay. In our example, the source address would be S. So the first initiator node, so the node who sent out the first route request. Okay. Then I have the sender address, which is basically the node, sorry, the address of the node which I've received the route request from. Okay, let me go back. So let's assume that we are here. We are node F. Okay, the source address is S. Okay, the sender address is E, because F has received the route request referring to S from E. So let's say it's the previous hop in the route request propagation. Okay? And is exactly the address which you are using to maintain the backward path. Okay? Because it's the one, it's the node you have actually to send the route reply to in case you receive a route reply for that specific route request. Okay? And then you have two, let's say, parameters which refer to the cost, so which refer to the quality of the path forward and backward, which each node uses to decide whether a route request or a route reply message has to be forwarded or dropped. So these two parameters are used actually to, let's say, decide which is the best path forward and backward, okay, depending on the specific context of the node. Okay? The forward cost is the accumulated path cost, okay, from the route request up to the node we are in. Example. Go back. Suppose that our metric here is number of hops. Okay? And suppose that we are here, node F. Okay? Node F has a forward cost of 2 because the route request to reach node F as flowed through link SE and EF, and if again we are assuming that the matrix for routing is number of hops, okay, the forward cost is just two hops from the originator of the route request, okay. And the residual cost is the other way around, okay. So it's the cost, current cost, from the current device, okay, to the destination of the route request, which is the cost used to backpropagate the route reply, okay. So two measures to measure, let's say, evaluate what is the cost for the path from the source of the route request to the current device and from the current device to the destination of the route request, okay. So that's the building blocks for the AODB routing, okay. Let's see how these building blocks are used. So suppose that we are in the route discovery phase. So we are sending out route request, and a route request message is received is received by some device, okay. So the first test we do is to check whether we already have an entry for that specific route request in our route discovery table. Okay. If we already have an entry for that specific route request, means that we have received in the past a route request message for the same destination and from the same node. Okay? Clear? So the easiest case is no, meaning that we don't know, it's the first route request message we are receiving for that specific source destination couple. Okay? So in this case, what we have to do is to create a new entry in the route discovery table, okay, and to store in this entry the forward path, which is the cost the route request message has experienced up to the point it is now, meaning to the current device. Okay? Clear? Then, once we have this entry in the route discovery table, what we have to do is to check out whether the route request has reached to an end, meaning that whether the destination, which is specified in the route request message, is local, so it's the current device, okay, or it's one of its neighbor devices, okay. If yes, means that the route request has reached to an end, so the current device can actually issue back the route reply message, okay. If not, it means that the route request has not reached to an end, which means that the route request must be rebroadcasted, okay. And before rebroadcasting, the current node has to create a new entry for the routing table, okay, labeling this entry as discovery underway, okay, which is specific for the destination of the route request message. Okay, so it pre-creates a line in the routing table saying that this is a new network address someone wants to reach, and I'm trying to discover what is the next stop. Okay, clear? Okay, so this is the no part. The yes part is an entry for that specific route request message already exists, which means that we have already received previously a route request message for the same source destination pair, I would say. So from the same source requesting the same destination, okay? So the test we have to do is to check whether the new route request comes from a path which is better than the one we have stored, okay? If the answer is yes, we have to update the line of the route discovery table, okay? And then we go back here to this case, to this branch here. If the answer is no, meaning that what we have already in our memory, okay, is the best path for that specific source destination pair, okay, so we just drop the route request message. So we do nothing basically. Okay, clear? That's for route request transmission. That's for route setup. So meaning this is the case where we are actually receiving a route reply. Okay. So if we are receiving a route reply, the first test we have to perform is whether there is an ongoing route request phase at the current node. Okay, so in other words, is the current node involved or not in this route request, route reply process? Okay. If the answer is no, it's just the route reply which is received by accident, so the route reply is dropped. Okay. If the answer is yes, means that the current node was somehow involved in the route request process, so has some trace in its own tables that there is this process ongoing. Okay. So the test it performs is whether the local node is the destination of the route reply, meaning that the local node is the source of the route request process. Okay. If the answer is yes, okay, let's say the final what do you call it? The end, the result is that the current node, which is the source of the route request process, will update its own routing table, okay, and then it will basically signal as a next stop the proper next stop, which is specified by the route reply message. Okay. If the answer is no, it means that the route reply has not arrived to the destination of the route reply itself, so it's not got back to the originator of the route request message. Okay. So what this node does is to check whether the residual cost of the route reply it has received, okay, is better or worse than what is stored in the route discovery table for that specific route reply message. Okay. So the answer is no, meaning that this node has already received the route reply message, which for the same route reply pair, okay, which has a lower cost or higher cost, then the route reply must be dropped. Okay. If the answer is yes, it means that the route reply which has been received, okay, comes from path, okay, which has lower cost than what's stored up to this moment. Okay. Then what the node does is to update the entry in the route discovery table, okay, to set up the next stop in the routing table, okay, and then to forward the route reply message backwards according to what is stored in the tables themselves. Okay? So that's just how all the concepts which you have seen at higher level are implemented in ZigBee. Okay? One very last slide on the routing costs. Routing cost is basically the sum, the cost of a route, the cost of a path, what we have called residual cost or forward cost in AODV implementation, is actually the sum of the cost of all the links which are involved in that path, so which build up the path. Okay, that's a very, very standard definition for defining costs in any routing protocol. So you just take all the links which belong to that path and you sum up all the cost of these links. Okay. That's not the only definition. There might be other definition of cost of a path, like take the maximum cost of all the links of that path, or you take kind of different average of the cost of the links of this path. But anyhow, we stick with the classical definition where you take a path which is composed of L links, okay? You sum up the cost of all the links, and this is the cost of the path, okay? And that's exactly what does ZigBee. So ZigBee just uses this classical definition of route cost or cost of the path. The point is, what is these per link costs? So which are the metrics which identify the quality of a link? Okay. So in ZigBee, basically, there are two metrics which are suggested. Okay. The first one is just the hop count. So you just count one link, okay, as with a constant of cost. For example, the constant here is set, which means that all the links just contribute to the cost of a path with a quantity which is equal to 7. Okay? Don't ask me why 7, because I don't know. It's just like saying just count up the number of hops. Okay? The second proposal for weighting, so for assigning cost to links, is given by this expression here, okay, which depends on this P of L, okay, which is exactly the packet reception rate, okay, over that link. So basically, the first metric is quality agnostic. So it just counts up the number of links in one path. The second metric has a dependency on the quality of the link, and the quality of the link is measured as the probability of receiving one packet. Okay, so the higher the probability, okay, the lower the cost for using that link. Okay, this is inversely proportional to the probability of receiving a packet. So the higher packet reception probability, the lower the cost of the link, so the higher the probability of using that link in a shortest path kind of routing. Okay? Again, this is standard. Okay? As we will see, other routing protocols in other wireless sensor network implementation use different kind of metrics. Okay? What is true for most of the routing protocols, most of the routing protocols for sensor network, they are based on the shortest path principle, which means that you decide what is the metric for weighting your link, okay, number of hops, quality in terms of packet reception probability, and so on and so forth, latency, and so on and so forth, okay. But then, once you have decided your metric, okay, the paths are computed according to a shortest path rule, which means that you choose the path which has the shortest cumulative cost with respect to all the others. That's, I would say, semi-standard in most of the sensor network implementations. Okay? Again, these are the two metrics proposed by ZigBee. Okay, so I guess we are over. I'll see you next week. Still, we have Wednesday with practical activities on operative systems, and then next Thursday we go on with ZigBee and 6LoWPAN. Okay?